Okay.
Yes, thank you.
So, ladies and gentlemen, online also to you. Hello, good afternoon. Oh, good morning. So let's use the time until the fire alarm goes off. To introduce myself, since I'm not an integral part of the consortia of ZeroAMP yet, and there's also external guests. So my name is Stefan Ernst. I'm at X-FAB, at X-FAB Group, in charge of new business development and strategy for the NEMS division. So I'll show you a little bit about X-FAB. I think it's a good point to introduce the company and as a background for you to understand why certain statements in the main part of the talk come about, how we look at the things. I think that's important. MEMS, as in electromechanical microsystem, have been around for quite a long time in the heart of the industry. They are all over the place in many value chains. They're in present their reality in many aspects of our daily life. Smartphones have dozens of those things, microphones, accelerometers, and all the kind of things. Maybe even some of them come from X-FAB. Your car has dozens of them. We have seen that. Very likely, some of them come from X-FAB. So talk about MEMS, NEMS, you may think, well, what's the big difference? Just make it a bit smaller. It's just one more letter in the alphabet, going from M to N. The point I want to make here at the beginning, the starting statement of my talk, which we'll find back later on, is even though, is that a fire alarm? No. Never mind. Even though there may be similarities of two things you look at, one looking like the small brother of the other one, things may turn out to reside in complete different worlds, right? So microtechnology and nanotechnology may differ in a lot of aspects. There's a lot of additional or different types of challenges. However, also to turn it around, there's much different types of potential. You can see other things. Here, the example with DNA, you cannot use a 2-inch wrench to fix a 1/4-inch screw, right? That's the point here. Now, before going, and I'm going to talk about both potential and challenges. I'm going to do that in a, let's say, a bit wider scope from the X-FAB point of view, trying to maintain always the context of the ZeroAMP. Also trying to, give recommendations here and there. What from our point of view makes sense to keep in the back of our minds. Before that, I'm going to go into introducing X-FAB. Who are we? X-FAB has been around for, you may have spotted it in the first slide already in the logo. This year is the year of our 30th anniversary as a foundry. If you calculate back, that's 1992. That's shortly after the Berlin Wall came down, actually. So X-FAB has evolved out of the, let's call it, remainders of the Eastern German microelectronic industries ecosystem, and has evolved into a globally operating silicon foundry, pure play foundry. With today, there are 6 production or manufacturing facilities worldwide, 3 out of them being in Germany, 1 in France, Corbeil-Essonnes, that's south of Paris, 1 in Malaysia on Borneo, and 1 in the United States in Lubbock, Texas. The German sites are Erfurt, that's the headquarters of the X-FAB group, and that's where also the wafers, which were mentioned by Dinesh earlier on, are actually made, the spurious XI10 technology. And this is a mixed mode CMOS and MEMS facility. There's another CMOS facility in Dresden, Germany. Dresden is nowadays evolving as one of the microelectronics centers of Europe, with Infineon, Global Foundries, Bosch, and so on. So this is a nice company to have, let's put it that way. And finally, it's written here, it's in the north of Germany, Itzehoe, that's north of Hamburg, that's a MEMS facility, which we cooperate with the German Fraunhofer Society. As I said, 6 facilities with round about 4,000 employees, most of them, of course, in manufacturing, but also with heavy focus on engineering and all the supply disciplines. The total capacity, if you look only on the demo slide of things, is around about 100K 8-inch equivalent wafers per month, excluding MEMS. MEMS is around about, what are we doing, like 150K wafers per annum, round about 8-inch equivalent. So it's I would say it's a high volume foundry. I'm going to show you a bit what we are doing there and what are the applications. Why do I emphasize that? As a foundry, as a high volume manufacturer, you have to have a different type of look onto development programs like this one. You have to basically, you're determined to think from the end, right? And this will this motivates why certain statements come as they are, right? Maybe one thing important to mention is that all our sites, all X-FAB sites, are automotive qualified, so automotive quality system. And this is mainly due to the fact. Maybe I get to go to the next slide here. Where are our customers in the industry? 50% of what we are doing ends up in the automotive supply chain. 50+%. With all the headaches which industry, I think, Signora Ceccarelli mentioned it earlier on, it is as it is at the moment. And if you're dealing with automotive customers, this is about 3 things. This is about quality, this is about quality, and this is about quality, right? So this is why this whole discussion around reliability and things which will occur later on, and which this is of central importance for us. Industrial, I think X-FAB has a strong stand with industrial customers, and I see, there's a lot of focus in this project on applications, potential applications which play in this field. What is, I think, unique about X-FAB is that we are in a position to support very long lifetime of products. So if you're an automotive or industrial product, it needs to be there for 10, 20, 30 years or something like that. So a long life cycle, even though many industrial applications come in, let's call it moderate wafer volumes, which is a challenge for the foundry. So standardization is key. Peers mentioned that already. An emerging market for us, and emerging means starting from a low level with very high growth rates, is medical, for whatever that may mean. That's in German we would say Worthülse. That's just a vessel to map any kinds of bio-ish applications inside. I'll come to that in a minute, but this is really where we see a lot of growth potential. On the consumer and communication space, we are meanwhile becoming very selective, and the reasons have been also lined out in the first talk. It's a very competitive environment going into all these edge computing, high performance computing type of things. That's not. I mean, we are entertaining some of this business, but not prime. That's not our DNA. Is automotive. Let's put it that way. So on a very high level. Sorry for that. You're all technology people here on a very high level. What are we doing? I mean, our bread and butter is CMOS and SOI technology. I'll show that in a minute. That's maybe 85% of what we are doing within X-FAB. All of that in an automotive context. MEMS, in the sense of classical MEMS, there's something moving, really mechanical system. I'll also tell something about heterogeneous integration. This is an emerging topic, and I saw that in all of the 2 slide decks before. This is something, I have one slide to line out how we look at the topic. This is something which is becoming more and more important, and wide bandgap materials. So this is in essence, the portfolio. On the CMOS side, how to look at it, I think the uniqueness of what we are doing here, probably if people have been working with X-FAB, they know what I'm talking about, is actually in this matrix there, which spans basically on the y-axis. This is nodes ranging from very old and mature technologies, which we still entertain for, especially for long life cycle applications, 1 micron, 0.8, 0.6. By the way, this is where the wafers come from, down to what is available currently is 110 or 30 nanometer. We are working here not on the leading edge or bleeding edge, 28, 14, 5 nanometers. This is analog mixed signal technology. There's no point in going, to the leading edge. So, and on the x-axis is basically let's say the combination of, or the flavors of all of these technologies available within one or within the portfolio of the technology. So modular analog mixed signal, including digital analog mixed signal, high voltage being something between 20 and 750 volts on chip, non-volatile memory, RF, optos sensors, SOI, high temperature in the automotive context, so 175 centigrade, and NEMS integrated or discrete. On the NEMS side, what are we currently working on? So it's not the strategic topics, that's what is reality. Again, most of the time it's the very left-hand side pillar, which is classical NEMS sensors, pressure sensors, accelerometers, gyros, thermopiles, gas sensors. This is also the field where my colleague Christian is working, and this we have I think a very solid footprint in the industry, especially also in the automotive field. If you go from left to right, so what is behind all these bio things, which I started to try to mention. So what we are looking very intensely into is on-chip integrated microfluidics. That means think of a silicon chip which has an interface directly to some kind of bioliquid, some analyte coming on top. Keywords like lab on-chip, DNA sequencing, on-chip ELISA testing, and things like that. So e-health and related, so analytics and diagnostics. I mean, the challenge here, or just to give you a spotlight, the challenge is if you're operating a chip not in a plastic mold, but an open package, and put some very aggressive stuff like a salty buffer solution on top, you can figure that's a different type of pipe. Wafer level integration and packaging, that's basically wafer bonding, wafer integration. This is through silicon biotechnology, especially on thick wafers. So electrical feed through sensor wafers or something like that to decouple front side with sensors or microfluidics with the electrical backside. Thin film piezoelectric materials. This is CMOS compatible piezo. Thin film piezo materials, aluminum nitride and the likes. I just mentioned that here. Here's one glance, and I come to a little bit more detail on the next slide to this topic. I should speak up. Heterogeneous integration. We started to look into chiplet technology, and the motivation comes on the next slide. There is a technology which we invested in over the last couple of years and which just is at the brink of being industrialized. It's called microtransfer printing. Think of a chiplet being released from one source wafer and in a massively parallel way being transferred to a destination wafer. Could be alien material. Think of a GaN switch being implemented onto a CMOS Think of a high temperature memory being printed directly onto whatever else. Think of a chip being implemented onto a flexible substrate. So whatever onto whatever, which is in round and shiny shape, so to say. And of course, we are always entertaining, we are entertaining customer-specific processes which don't fit anywhere in here. Just this one slide, because I think it has this whole topic of heterogeneous integration has an angle into the technology here, and in fact, it occurred on the slides and also in the CHIPS Act slide. So what is reality is that for decades, the evolution within the STEMI space has been determined by Moore's law scaling, so from evolution from one node to the next one. This has been observed to flatten out somehow. I mean, well, one has predicted the end of Moore's law already decades back, but that's the reality is that it really flattens out, also because of the exponential growth of the financial figures, which are related to the next node. I mean, at some point you arrive at a single atom. So what we see, and we really see that in reality, is a shift, paradigm shift in the industry away from Moore's law transistor-based scaling to scaling by on the system level, right? And this is mainly driven by the usual suspects, high performance computing, IoT, mobile, and so on. But it also starts to arrive in sensor system, in biomedical, in automotive. So heterogeneous integration refers to integration of separately fabricated items onto one wafer. So it's a wafer process which uses MEMS, CMOS, whatever subsystems, and integrates them to a certain level onto one die system in package. This is what we are looking into, especially on the chip and device level. However, also the borders between chip and system kind of getting fuzzy. Okay, coming to NEMS technology. So you know probably much better than I do where it all came about. I mean, NEMS itself has been around. The idea has been around for quite some time. In the early 2000s, the millipede chip by IBM was the first real demonstrator of a large-scale integration memory device based on NEMS, where I would say NEMS being a nanotechnology being anything, real nano, I mean, below 100 nanometers, let's put it that way, or even smaller, depending on whom you ask, probably. Now, what is the aspects we look at nanotechnology and NEMS? Why should we even think about it? And I listed four pillars here, from which have an angle pointing into the nanotechnology and NEMS direction. MEMS, of course, I mean, if you do MEMS, then make it smaller, make it higher, with a higher degree of integration, you automatically end up at smaller nodes. That's pretty clear. Mixed signal ASICs, including digital logics. I mean, Piers and the team have talked about enhanced operating conditions and all the like. I don't want to repeat that. This is a completely different view angle in terms of how to. It's not about militarization. It's about extending things which are there to explore new applications. That's what we see. Nanotechnology is about functional material, and here in this context, I think this NCG can be seen as a innovative nanomaterial. You can start to you can realize different types of device concepts, and I'll come to that in a minute. And this advanced packaging and heterogeneous integration, it has also an angle into being able to integrate higher integration devices, right? So I think there's a point to watch out here. So I want to start looking into NEMS and nanotechnology for a field which we are currently, where we are actively looking into. This is for the field of bio applications. This is not all about real NEMS in the sense there's mechanical systems, but NEMS also means, or nanotechnology also means, non-CMOS compatible manufacturing methods, funny materials, strange manufacturing processes and things like that. So please don't expect something moving here. Nanopores, solid state nanopores technology, that's reality already. It's in the market. Next generation DNA sequencing, we have that. The next step will be really solid state nanopores, meaning tiny little openings in the nanoscale manufactured in solid state membranes, which act as single molecular detector. Think of a DNA or protein pulls through a hole. You can build basically impedance, voltage dividers, if you will, in terms of the electrical, the fluids drive through a hole, and then measure electrical quantities, single molecules created by passing this hole. This is determined to come. This is becoming reality in a couple of years. Low-dimensional materials. So I listed them here because it's also about nanotechnology. We're looking into graphene and related materials. Carbon nanotubes and 1D materials is currently not in our focus, however, something to watch out. I'm pretty sure. And here it's about, in the bio context, it's about realizing enhanced sensor performance for lower SNR and these kind of things, higher stability. And so, nanoelectrode arrays. This is also, is just becoming a reality as we speak. Let's put it that way. Microelectrode arrays. Think of a chip surface where you grow cells, organoids on chip to really measure cellular activities and so on chip. Context is pharmaceutical development and these kind of questions. So this is getting more and more into nano world, let's put it that way. And finally, real NEMS, any kind of cantilever-based NEMS type of devices. So think of beams which are functionalized and can basically do something like force spectroscopy on single biomolecules which dock onto the cantilever. Highly interesting, highly challenging piece of. I wanted to. How long do I have time?
Another 10 minutes.
Okay, then I go through that rather quickly. I wanted to elaborate on atomic layer processing because this is something where X-FAB is particularly looking into. This is not reality as yet. I mean, it's there. It's on the market. It's commercially available. X-FAB is looking into having these capabilities in house. And I think it has an angle into this project as well, I would say. So what is atomic layer deposition? It's basically, think of a cyclic process where layers grow really on the atomic, it's a self-limiting process. You purge a precursor, and there's a surface reaction covering the whole surface conformally around any edge. So irrespective of topography, and in a cyclic process, you're able to really grow layer by layer. The equivalent on the patterning side is atomic layer etching. This is less mature technology as yet. This is basically a method to have a self-limiting way of removing single atomic layers. So it's a very fine way of patterning atomic surfaces. Few examples on the MEMS or NEMS side. Examples, especially from Fraunhofer EMS in Duisburg. You can use that as sacrificial layer technology to really make very well-defined layers, which then are removed to build cavities. Here you see a 3D membrane, which they, I think, use as a micro scale. So it's really a free-hanging thing with a nanostructured membrane or freestanding nanowires for gas sensors here on the left-hand side. Of course, very conformal and thin coatings, and here's the angle into ZeroAMP. It's used, this example is used for passivation, but you can also use it for functional layers. Nanostructured materials, either laminates or porous, I think that's self-explaining. Okay, now let's come into NEM relays and switches. I listed down a couple of points which basically point to the individual device and which should summarize some of the advantages we see from the technology or the application side. And Dinesh, feel free to hook in and to jump on the topic, or we could do that afterwards. Of course, low leakage has been mentioned already. One particular example which came up during discussion within X-FAB for IoT applications, power gating, so applications which depend on a power source. Of course, it's very important to preserve or to extend lifetime power source as long as possible, especially for low duty cycle applications where you have long sleep times in between the cycles. So you need time either for energy harvesting or to preserve the battery or the supercap. Another point is namely here that if you can replace the battery by capacitance, which is high temperature compatible, you can enable different types of applications. Low power consumption in itself, reduced switching losses, parasitics, and can integrate multiple frequencies on chips. That's relevant for RF MEMS. Extended operating temperature, this has been mentioned. One thing I would like to highlight here is that we see the real benefit is high temperature can be present over the whole lifetime of the device. In a typical automotive qualified CMOS technology, you have a duty cycle. The chip is never over 10 years, 30 years at high temperature. Right? Yeah, high voltage. If you can build a MEMS or MEMS drive or level shifter, you can have the slides afterwards. If you build a level shifter and you are really able to switch high voltages on and really off, this is an advantage, I would say. On the digital and logics, I don't want to repeat the story again. I think that was a very comprehensive. I mean, you saw the figures already there. For the sake of time, I can only support. If this becomes reality in products, this is a good thing to have. Now, let me spend 2 slides on industrialization challenges, and I think that's important to go through them and also for the consortium to understand how we look at it. First, let's look at process technology. I think the key here is, as you know, with the technology we have today, is really the functional materials. This applies to NEMS in general, but here in the ZeroAMP, this is the NCG material, this is the contact material. So I think where we need to pay attention to is really process maturity and compatibility to existing manufacturing environments, and eventually scalability to high volumes. And I come to that. This has a technology angle as well as a commercial angle. It's clear, right? Performance characteristic. This is self-explaining, like contact resistance, sticky versus non-sticky contact, reliability. I think this is key, and there's a strong recommendation to really focus as much as possible in characterizing this contact material, which of course, how many switching cycles, how much is the wear out, and things like that. Can we reach, or can we expect to reach 10 to the 7 cycles? How about for an NVM? How about data redundancy and things like that? So the recommendation is really this is a key aspect which will come along very early in the product development. I think you agree. It's not very something very new, but just want to reiterate that. Process integration. What I mean by this, we can look at things from the single process point of view, but what we're doing is it's an integrated process, and the processes talk to each other. One example is the high temperature NCG deposition. Any process which is coming before that has to be high temperature compatible. So show me the process which is at at nano level, which has a very high temperature stable metallization. It's not trivial, right? There's other aspects we could and we should talk about. This needs to be taken into account. I mean, this is probably not so much bothering us for demonstrator, but if you want to include that into or implement that into an integrated product flow, this will be very important. Existing manufacturing ecosystem. One particular point is the cross-contamination management. If you have a random fab, you always need to be very sure what kind of material, what kind of wafers you take into your fab in order to have no cross correlation or cross dependencies of the flows. By the way, any of these subjects would be a talk by itself probably. So I just leave the headlines, right? Process control, Q gates is of course for product. This is essential. There's no use of a good process if you can't control it well. I think you mentioned something like that as well. I mentioned these terms, for the foundry, that's a commercial aspect, right? I mean, what can you need to be sure that you can basically manufacture to a specification, which is however it may be defined, and just be sufficiently sure that you can throw the wafer over the fence and whatever comes out works, right? I mean, you cannot do 100% testing if you're on mass manufacturing. You have to rely on your Q gates and that the specifications are well. Further challenges, there's missing the word challenges. The application view, I think we discussed it already in the dinner yesterday. And we need to be able we need to have the system architecture in the back of our minds. It's not expected to be a plug-and-play solution for anything. We need to think, let's say, we need to think system, whatever that may mean for the individual technology. And of course, ecosystem for design and supply. Clear. I mean, there's no. Who said it? There's no point of building a new fab for 2 or 3 devices, right? You have to be able to implement it in existing, or well, not existing, but it has to go into the semi-supply chain as this, which also has to evolve. That's clear, but not every generation can commercially stand that. On the commercial side. 2, 3 comments. The applications which are, I mean, there's a high possibility that there is applications which will really benefit from this technology. I'm pretty sure about that. The dilemma is the more special your application case is, the more you're moving in a niche, right? And this is of course. A niche doesn't mean that you can do things somewhere in a lab. You still need quality. You need to be sure that it's a product. It's not a demonstrator, right? So you basically need the fully industrialized process anyway, right? And here comes the challenge for the manufacturer. How can you? I mean, how do you manage the invest necessary to implement it really into a foundry process? For high volume, I mean, this challenges the foundry model, right? And the solution is the buzzword platform. It's really standardization. If you can basically find a platform where you can have a differentiator by design and not by process, by design. So I mean, this is a good example of it. Presumably, if it works out as a lateral switch, not an in-plane, out-of-plane switch, you can basically. If you know the materials well enough, you can expect that with all the EDA environment implementation, you can have such a scalable approach. Right? For high volume application, I'm pretty sure we need to go to 300 millimeter to smaller nodes. Significant invest is envisaged. How to deal with that? Piers, we had a long discussion about it yesterday night, and I think this is a process through which we all need to go, and just highlighting that here, that's pretty normal. If something new comes up, I mean, this may sound very negative here, but that's a pretty normal process to go through. Cost of quality, that's also clear. So, conclusion. I mean, we have seen that for a number of reasons, this is a promising technology, either for efficiency gain, extended operating conditions, advanced architectures, and it's still at a very early phase. It's a task really to come from TRLX to TRLY. And I've outlined a number of challenges for this industrialization, but please, you know, I put my black hat on. However, it's also time to think about this very early from the end. So if we can basically build a technology roadmap out of that, which takes these challenges into consideration, and thanks for giving me the chance to outlining that very early on. I think there's a chance to make this successful. So we need the application, we need to map the application and the technology roadmap together. Thank you.
Yeah, no, we started a bit late, but thank you very much for your talk, Stefan.
Question?
If there is like a short question, we can address now.
Otherwise, I'm going to be here for the rest of the day. So.
Yeah, pretty sure this talk is not just answerable with one.
Yes. I'd be surprised.